All right, now that we are set up and ready to go, let's talk a little bit about buffers. So before we start talking about buffers, we're going to talk about the common ion effect, which we will talk about again later when we talk about solubility. But for right now, common ion effect, when a weak electrolyte and a strong electrolyte that contain a common ion are together in solution. This means that the weak electrolyte will ionize less than it would if it were alone in solution. So how this is working, this is really going back to Le Chatelier's principle, right? Remembering that when you make an adjustment to an equilibrium, the reaction is going to work to counteract that adjustment, right? And so we're going to treat the dissolving of weak electrolytes as equilibrium situations because that's really what it is. And so by adding more of your product, right, in this case the common ion, the equilibrium is going to be pushed back towards reactants. So we're going to look at this with an example. So the pH of a solution that is 0.1 molar hydrofluoric acid, which is a weak acid, and 0.1 molar sodium fluoride. This has a Ka of 6.8 times 10 to the negative 4 for hydrofluoric acid. And the pH, keep in mind that the pH of this solution with hydrofluoric acid alone is 2.1. So, first thing we're going to do, we're going to write down our balanced equation, which looks like this, right? We have HF in equilibrium with a hydrogen ion and a fluoride ion, all aqueous. And then we're going to utilize everyone's favorite chemistry tool, the ICE table, and fill in our values. So when we fill in values of the ICE table, and I draw all over it, keep in mind that the concentration, the concentration of our hydrofluoric acid is 0.1 molar. The concentration of our sodium fluoride is also 0.1 molar. And what this means is that because this is a very soluble ionic compound, that means that the concentration of both sodium and fluoride are going to be 0.1 molar to start out here. But the one that we're concerned about is fluoride because it is a common ion. So initially, right, we also have 0.1 molar concentration of fluoride in our solution, right? So the 0.1 molar for hydrofluoric acid comes from here, and the 0.1 molar for fluoride comes from here, right? So that's why we start out with some of our products in this case. And so then as we change, right, we're going to be dissolving or dissociating some of the hydrofluoric acid, which means we're going to be making hydrogen and we're going to make more fluoride, right? Because when this breaks apart, hydrogen and fluoride, so we have 0.1 minus X, X, and 0.1 plus X. All right, then after that, we can write our equilibrium expression for the dissolution, where we have products over reactants. And after we write that, we can fill in some numbers. So it will look like this. Now, here's the deal. We can simplify this even further now because those X's, so if you notice, the Ka value is less than 5% of our concentration here, which means that this value, whatever it is, will not affect our concentration in any noticeable way. So what we're going to do, because that Ka is less than 5% of our concentration, we're just going to get rid of the X's in this calculation. Now, you will notice here, or hopefully you notice here, that our concentrations are now exactly the same. And because they're divided by each other, we can get rid of them. and make it look like this, which is great because now our Ka equals X. So we don't even have to calculate for it. It's already given to us. And since that is our concentration of hydrogen, we can just take the negative log of that, and it will give us our pH, which in this case is 3.17. All right, you'll notice that that is higher by quite a bit compared to the pH of hydrofluoric acid on its own, right? And this is because we're treating it as an equilibrium situation where if we add products, right, specifically fluoride, we are pushing the equilibrium back this way, and less of our hydrogen fluoride is going to dissolve. So that brings us to buffers, because what buffers are a solution that contains a weak conjugate acid-base pair, just like you saw in that last example, and this allows the solution to resist changes to pH when a strong acid or base is added to the system. Now, here is a really important equation for buffers, the Henderson-Hasselbalch equation, where we can equate pH to the pKa, and remember that is just the negative log of Ka, plus the log of our conjugate base concentration over our acid concentration. Remember, and this is good to remember that this is the conjugate base over our acid. Right, so when I say base, I'm talking about conjugate base. And so that equation is going to be very helpful when we are looking at the pH of buffers. So a quick note, just like with non-buffer pHs, right, like we talked about in our acid and base video, if the Ka is 5% of the concentration or greater, Hasselbalch cannot be used, and you will need to calculate the concentration of hydrogen using the quadratic equation. So it is time for some more examples. So in this one, we're going to calculate what the pH of a buffer is, that is 0.12 molar acetic acid and 0.1 molar sodium acetate, right? So here, right, acetic acid, that is acid with the acetate ion, C2H3O2 minus, and sodium acetate that has the same C2H3O2 minus, right? So here we have our acid and our conjugate base, and that means that when we have both of those together, we have a buffer. So we're going to look at the Henderson-Hasselbalch equation here because, right, if we look, the Ka value is definitely less than 5% of our concentrations here, right? Less than 5%, so we can use our good friend Hasselbalch. And we can put in some numbers here, right, because we know we can calculate the pKa, right? Just take the negative log of 1.8 times 10 to the negative 5, and that makes 4.74. And then we take the log of 0.1 divided by 0.12, right, because it's conjugate base over acid. And we get a pH of 4.66. Great. There we go. That's how you calculate the pH of a buffer solution. Pretty simple. So now we want to see what the pH of this is after adding 5 milliliters of 2 molar sodium hydroxide, which, as we know, is a strong base. So what we're going to do, we're going to start by writing an equation where we have our acetic acid reacting with the hydroxide from our sodium hydroxide, and we are forming acetate and water. We are then going to make an ice table in which we put in our concentrations. So if we remember from the last problem, the concentration of our acid was 0.12, the concentration of our sodium acetate was 0.1, and right, if we multiply 2.0 mole per 1 liter times 0.005 liters over 1, or yes, so okay, that's where I should back up. We want these in moles, right? We want these in moles. So we're going to convert all these to moles. So the first thing we can do is assume we have 1 liter of solution. There, that's where I'll start. We have 1 liter of solution. So because our concentration of our acid was 0.12 molar in the last question, 0.12 molar of 1 liter, and we get 0.12 moles. Same with acetate, because our concentration was 0.1 molar. If we assume we have 1 liter, we will have 0.1 moles. Here, right, we get our 0.01 moles because we know that we have 0.005 liters of a 2 molar solution, which when you multiply those together gives you 0.01 moles. So then we say that because these two are reacting, right, they are going to react, they are going to be used up, so we are going to lose our 0.01 moles of hydroxide. We are also going to lose 0.01 moles of acetic acid. And we are going to gain 0.01 moles of acetate, right? Because these two are reacting with each other to form this. Which means that at the end we have 0.11 moles of our acid left, and we have 0.11 moles of our acetate. So now that we have our equilibrium moles, we're going to put those in our Hasselbalch equation, and you'll notice that we have moles divided by liters here. And this is really important, right? So I'm going to draw like 3 arrows to it, maybe even a 4th arrow, or actually that's 5. So 5 arrows to this, because it's really important that you remember when you are looking at the equilibrium of this system, you have added volume to your system, right? And it has to be accounted for when you go to calculate the concentration of your acid and conjugate base, right? So we are going to put in our new volume here that we're going to divide our moles by. And I think probably some of you are out there saying, but why are we even worried about that? Because our numerator and our denominator are the same. And in this case, you're correct. They are the same. So in a second, we're going to ignore all this stuff that I've been talking about. But for right now, I'm going to say it one more time. You have to account for the change in volume when you go to calculate the pH of your buffer system after you have added a base or acid to it. Okay, now, having said that, I will say, yes, you're correct. We can just ignore that because those are both the same. It will be the log of 1, which, as all of you math wizards know, is 0. So we just end up with a pH of 4.74, just like earlier in this video when we could ignore this whole section and the pH is equal to pKa. Okay, there we go. That is buffers. That is calculating with buffers. and I'll see you in class.